Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button. Welcome back to Lecture 2, Calculus 1. This is on tangent lines and the derivative. So let's start with what exactly is a tangent line. And I think the easiest way to get a feel for a tangent line, we can always construct a tangent line if we take a circle, let's say of radius r, and I'm going to give it an orientation along here such that it makes an angle theta with this. Right? So this leg here is r cosine of theta, and this portion here is r sine of theta. Little review from trigonometry. So the point P right here will be located at x value r cosine theta, y value r sine theta. You guys should be familiar with that, yes? Yeah. So now I'd like to construct this line, this radial line that I've drawn here. Well, it's starting, we'll say that the origin is right here at the center of the circle, right? So it's really just going to be a line that says, you know, y, and I'll call it sub r for the radial line, equals some slope m times x, right? Well, what is the slope? Well, the slope is the rise over the run, and so you can see that that's just going to be r sine theta over r cosine theta. The r's will cancel, and so we'll just get sine theta over cosine theta, but that's just the tangent of theta, right? So that's tangent of theta times x. So now that we have an equation for the radial line, can we construct a line that is perpendicular to that radial line? Who remembers from algebra what is characteristic of a perpendicular line? A line that is perpendicular to this radial line will have what slope? Anyone remember that?
Like 1 over?
Well, it's 1 over. It's minus 1 over, though. It's in, yeah, so the tangent line, right? Well, let's write it like this. I'm going to write this as m sub r. So m sub r, this the slope of the radial line, is the tangent of theta. The slope of a tangent line, well, this, I haven't got to the tangent line part yet, but the slope of a perpendicular line to this radial line will be equal to minus 1 over m sub r. So that's going to be equal to minus the cotangent of theta. Okay? So now I can construct a line through this point P. Well, for that we'll use the slope-intercept form of a line. And we'll write that y sub t, for that's because I'm going to call this a tangent line, and you'll see why it's called that in just a second. So y sub t minus its y value is r sine theta is equal to the slope, which is going to be minus cotangent of theta, times x minus r cosine theta. This is just to allow the line to pass through the point P, okay? And so what is that line going to look like? It's going to be a line which touches this circle only at this point P, okay? And that's what makes it a tangent line, is that it touches this curve only at one point. And so as we move, as we change theta, right, the slope is going to change. Also the intercept point will also change, and it'll move around this circle, right? Kind of like this, right? You can see how it just touches the edge of it, right? If we were to cut through, say, 2 points, like say those 2 points right there, that would not be a tangent line because it passes through 2 points. And so we call lines that cut like this, we call them secant lines. Lines that touch in only 1 point we call tangent lines. And so that's what a tangent line is, okay? So of what utility is this? Well, back in the early days, before Newton invented the calculus, people were worried about tangent lines for curves. So you might have some curve like this, and you might be like, well, what's a tangent line? You know, let's say this point right here, we'll call it P again. Right? They're looking for that line which just touches at that point P, right? And so the way that they could construct that was by finding a circle which fit just perfectly right there at that point, locating the center of that circle so that they could then construct this tangent line, right? And that would be kind of a pain, okay? Fortunately, we have better ways now. But this was the idea. This was the old way of finding tangent lines, and so I think that looking at tangent lines on circles is nice because it's kind of obvious, right? It's just always perpendicular to those radial lines. But let's talk about secant lines a bit now. There. So now I've got some curve. You can imagine that this is something like probably y equals x squared, right? We could very well say that it's equal to that if we wanted to. Y equals x squared, or f of x is equal to x squared. And we're cutting it at points Q and P. And P is going to be our point of interest, okay? And so this line that I've drawn through P and Q, right, we can find the slope of that line. The slope of this secant line, I'll write sub s, is going to be equal to the delta y over the delta x, right? That's the change in the y value over the change in the x value. And if y is equal to x squared, right, what's this equal to then, right? This is going to be this point Q. At Q, it'll be at x squared minus, I guess I want to let P be equal to some particular point. I'll let P be equal to point 1 comma 1, right? So when x is equal to 1, y is equal to 1, that's that point right there, right? So the change in the y value will be x squared, right? So this is a point x comma y. Actually, it's going to be x comma x squared, right? Because we know its functional form. And so it's x squared minus 1. That's the change in the y value, because this value here is x squared. This value down here is at 1. And the change in x, delta x, is just x minus 1. So x minus 1, yeah? So that's the slope of this secant line that we've drawn. What I'm interested in is the condition where Q, the point Q, approaches the point P. And so I can make a little table. We'll call it, I don't know, Q sub x. It means the x component of Q, right? And I'll write m sub s, the slope of this secant line, as we change these values, okay? And so when they say, if I choose x to be, oh, I don't know, what do I do in my table? We'll say 4. When x is 4, what do we get up here for the slope? Well, 4 squared is 16, minus 1 is 15. Divided by 4 minus 1 is 3, so that's 15 over 3, or 15 thirds, which is just 5, right? Yeah. If I decrease, I bring x closer in, and allow x to be equal to 3, let's say, what do I get? Now I get 3 squared is 9, minus 1 is 8, divided by 3 minus 1 is 2, that's 8 divided by 2 is 4. So the slope of this secant line is decreased, it's gone down to 4 now, right? If I bring it in even closer, say 2, well, 2 squared is 4, minus 1 is 3, divided by 2 minus 1 is 1, so we have 3 divided by 1, which is just 3, okay? I could even try, obviously I can't go to x equals 1, because what happens when x equals 1? But we could try some values like, say, 3 halves, that's 1 1/2, right? If x is 3 halves, then what are we going to get for the slope? The slope will end up being 5 halves. We could even try 5 fourths. That's 1 1/4, in which case our slope would be 9 fourths. So you see what it's getting close to, yeah? If it was 8 fourths, it would be 2, right?
Yeah.
At 1, of course, we don't know what the slope is. We could try from the other side as well, right? We could try at 0. Well, at 0, it's minus 1 over minus 1. What's that? That's just 1. But it just, looking at where this is headed, this is, approximately 2 here, right? So it kind of looks like our slope is heading towards 2, yes?
Yeah.
So if we had to guess, we'd say that the limit as Q approaches P of this secant line slope, right, looks like it's headed towards 2. Okay?
Okay.
It might help to graph these values, and then you could kind of see what this looks like. So if this is the slope of the secant line versus x, so here's 1. At 0, we found that it was 1, 2, 3, 4, 5. Let's move these in just a little bit. Say this is 1. So at 0 is 1. At 2, we had it pegged at 3. Let's go up to 3. It's obviously, looks like it's a line, right? At 3, we had, it was at 4. So if we draw this line through, I'll just adjust my dot so it fits the line. At 4, the slope was at 5, right? So it looks like the slope, yeah, that was fine. At 1, which is undefined, is headed towards 2, yes?
Yeah.
So if we look at this expression a little more carefully, what if I were to ask about the limit as x approached 1 of x squared minus 1 over x minus 1? Well, you may recognize the numerator as a difference of two squares, right? X squared minus 1 is just x plus 1 times x minus 1, right? So let's write that in. X plus 1 times x minus 1, all divided by x minus 1. And of course, we still need to take the limit of this. I forgot to write that in here. I'll just write lim. You see, the x minus 1s will cancel, and I'm just left with, right over here, the limit as x approaches 1 of x plus 1. Well, now I can plug in 1 for x and find that this is equal to 1 plus 1, which is 2. Yes?
Yes.
Okay. So this general procedure on how we turned a secant line into, you see, as it approaches P, the secant line is going to become a tangent line, yes? It's getting closer and closer to a tangent line. So I'm taking 2 points that cut the curve and turning those 2 points into 1 point. That's what I mean when I say Q approaches P. Okay? Does that make sense?
Yeah.
Yeah. So now I can write this tangent line if I wanted to, right? Passing through point P, we'd get the point P is at 1, 1. So we would get that y sub t minus 1 equals the slope we get from the limit here, 2 times x minus 1. And that would be an equation for a tangent line that passes through this point P, like that. Okay?
Okay.
So I just want to generalize this approach now, right? I want to state formally that the slope of a tangent line to a curve is equal to the limit as x approaches some point C of f of x minus f of c divided by x minus c. Okay? Another way to write this is that slope of the tangent line is equal to the limit as delta x approaches 0. Right? Remember, delta x was like when we moved q closer to p, we had these two values, the q sub x and then the value at p for x, right? As those approach each other, the difference in them approaches 0. That's what this delta x approaches 0 business is about. And we write this as f of x plus delta x minus f of x divided by delta x. So it's kind of two ways of saying the same thing, okay? So it may help in order to see this, to imagine what this looks like. So if this is my curve, here's a couple of points on it. This distance here is the delta x, okay? And the distance here is f of x plus delta x minus f of x, right? That's actually this distance here, my bad. See that?
Yeah.
So the line that we're constructing between these 2 points is given by the rise, which is f of x plus delta x minus f of x divided by the delta x, okay? So let's try to use this and do an example. Let's consider the function f of x equals x minus 2. And I want to find the slope of the tangent line at the point 3, 1. Okay?
Okay.
So how do I use this formula to do this? I'm going to use this one for this case. Actually, I'll do it both ways. I'll use both of these expressions up here. So I'll call it method 1. Circle that. I'll call this method 2. The slope of the tangent line using this method up here is going to be equal to the limit as x approaches 3 of, well, f of x, which is just x minus 2, minus f of c. Well, if I plug in 3 into this equation, I get 1, obviously. So it'll be minus 1 divided by x minus, our c again is 3, so x minus 3. And so what does this give us? This gives us the limit as x approaches 3 of x minus 2 minus 1 is just minus 3, x minus 3 over x minus 3. You see that those cancel, and that's just equal to 1. And so the limit as x approaches 3 is just equal to 1. Okay? So that's how we would get this limit in this case. If we use method 2, what would we do? Well, we would say the slope of the tangent line is equal to the limit as x approaches, or excuse me, as delta x approaches 0 of f of x plus delta x. So I have to write in, replace x with x plus delta x, and so that'll give me x plus delta x minus 2 minus f of x. Well, f of x is just x minus 2 minus x minus 2 divided by delta x. Well, if I simplify up here, what does this give me? Well, the limit, delta x approaches 0, x minus x, right? I'll get x minus x, that's from this. Then I'll have delta x plus delta x. And then I have minus 2 minus negative 2. Well, minus a negative is positive, so that's minus 2 plus 2. You can see that these two terms here just go to 0. And then we're dividing by delta x. And so what we end up with is the limit as delta x approaches 0 of delta x over delta x. But that's just 1. And so the limit is 1. Okay? Solving it two different ways, using this formula or using this formula. These, by the way, are called difference quotients. Okay? And so we're taking the limit of difference quotients. Now let me let you try one at home. F of x equals 5x plus 4 at the point 2, 14. Use either formula 1 or formula 2, but do use the limit of a difference quotient method that I just illustrated. So pause the video and try that now. Okay. So I will just do one of them. You want to pick your favorite, method 1 or method 2?
Method 2.
Method 2. All right, I'll do method 2 and show how what the limit of this is in that case. So the slope of the tangent line is going to be equal to the limit as delta x approaches 0 of f of x plus delta x. So I just simply replace x in 5x plus 4 with x plus delta x. So that's going to look like this. 5 times x plus delta x plus 4. You see how that worked? Just simply take the x and replace it with x plus delta x. And then I'll subtract from that f of x, but f of x is just 5x plus 4, and then divide that all by delta x. So I'll distribute the 5 and the negative sign, and what do we get? The limit as delta x approaches 0 of 5x plus 5 delta x plus 4 minus 5x minus 4, all divided by delta x. So you see that this 4 and this 4 cancel each other out. This 5x and this minus 5x cancel each other out. And I'm left with 5 delta x over delta x. So this is equal to the limit as delta x approaches 0 of 5 delta x over delta x. Delta x over delta x is just 1, and so this is just equal to 5. Okay?
Okay.
And you get the same thing the other way around. So the slope of the tangent line that we've been talking about, this is the definite. What is the slope of the tangent line? It is the thing in calculus that we call the derivative. Okay? So here's some notations. So these are different ways to write the slope of the tangent line. You can write it as f prime of x. That would be a functional form for the tangent line for a function f of x. Okay? You can also write it as d over dx, assuming that x is the independent variable, right, of y, where you have an equation y equals something in terms of x, d over dx of f of x. Sometimes people write y prime. If they have an equation y equals x squared, for example, y prime is the derivative. It's a function which tells you what the slope of the tangent line is at every point x, okay, in the domain. One other, sometimes you'll see a big D in a bracket like this, and then inside here f of x. Using this notation, I'm now going to replace these slope of the tangent lines with, I'm just going to call it f prime of x. Same thing for this one here, f prime of x. So that is the derivative. The derivative is nothing more than the slope of the tangent line to a curve, f of x. So let's use this one. I kind of tricked you before when I used this form to look at the slope for, I think it was like 5x minus 2, something like that. And it gave us an answer of 1 or 5. And so let me show you what happens. We can use this one to get the functional form, not just the derivative at a point, or the slope of the tangent line at a point, but at any point, okay? So let's try, it's a 2x cubed. Let's consider the function f of x equals 2x cubed. And I'm going to use this form. This is the form I would use if I was looking for the derivative at a particular point. This is the form that I will use or prefer if I'm looking for the derivative at all points. Okay? So let's see how it gives us that. So f of x is 2x cubed. F prime of x, or the derivative, is equal to the limit as delta x approaches 0 of f of x plus delta x. So all I have to do for that is just replace 2x cubed, not with x cubed, but with x plus delta x cubed, minus f of x, which is just 2x cubed, all divided by delta x. And this may be a good time to remind you of how to expand things like, a plus b cubed, right, in terms of, what is it called? I think it's called the binomial expansion, or binomial theorem, okay? And so how do I get these values for how do I get x plus delta x cubed? X plus delta x cubed. Well, the first thing you do is you write all the terms out, like x cubed, and then I'll have plus an x squared, and then plus an x to the 1, and then plus an x to the 0, okay, which is just 1, right? And then the second term, delta x, I start out at delta x to the 0, which is just 1, and then I'll have a term here which is delta x to the 1 times delta x squared, and then finally times delta x cubed, okay? So it starts out with the first term cubed and ends with the last term cubed, right? What are the coefficients that go on these? So they're just n choose k, right? So this is 3 choose 0. The coefficient here is 3 choose 1. Here would be 3 choose 2, and finally 3 choose 3. And if you don't remember the formula for this, n choose k is n factorial divided by k factorial times n minus k factorial. So the first term, 3 choose 0, right, is 3 factorial divided by 0 factorial. 0 factorial by definition is 1, right? Divided by 3 minus 0 is 3. So 3 factorial over 3 factorial is just 1. So that's 1. 3 choose 1. This time we would have 3 factorial over 1 factorial, which is also 1. Over 3 minus 1 is 2 factorial, right? So get rid of that because that's just 1. 2 factorial. This is like 2 times 2, 3 times 2 factorial. So the 2 factorials cancel, and I'm just left with 3, okay? And these things are always symmetrical. So this term and this last term, 3 choose 3, will also give us 1. And 3 choose 2 will give us 3 as well. So there's always a symmetry involved here. If you have an odd number of functions, then the one in the middle will be unique, and then everything else will be the same to the left and the right. But this is how we can write these terms out. So this is what this expands to. We have to multiply everything by 2. So times 2 makes this into a 6. This is a 6, and this becomes a 2. And then we're going to subtract off 2x cubed on the end, right? Well, that just cancels this out. So we get rid of this, we get rid of this, and we're left with just this middle piece right here. So that's what I'm going to write in right here. This is going to be the limit as delta x approaches 0 of 6x squared delta x plus 6x delta x squared plus 2 delta x cubed, all divided by delta x. I can divide this delta x into each of these terms, and what that's going to give me is 6x squared, the delta x is completely gone, plus 6x delta x plus 2 delta x squared. Well, as delta x approaches 0, there's no problem with setting delta x equal to 0 now, right? Because it's not in the denominator. Here, this goes to 0, this goes to 0, and all I'm left with is 6x squared. And so what I found is that f prime of x is equal to 6x squared. That's the derivative function. That tells me this. So if I want to know what the slope of the tangent line is at a particular point, like say x equals 1, just plug it in. Well, 1 squared is 1, times 6 is 6, the slope is 6. X equals 2, 2 squared is 4, 4 times 6 is 24, so the slope of the tangent line at x equals 2 is 24. Okay? Let me let you at home try one now. Okay, let's see how you did on that. So f prime of x is going to be the limit as delta x approaches 0. Well, this time we'll do f of x plus delta x to the 4th, so that's x plus delta x to the 4th, minus x to the 4th, which is just f of x, all divided by delta x. Now, the relevant coefficients in the expansion of x plus delta x to the 4th power, right? We'll obviously have x to the fourth. The next term is going to be 4 choose 1, right? So that'll be 4 over 3 factorial. So that is just going to be plus 4x cubed delta x. After that, we're going to have 4 choose 2, which is going to be 4 factorial over 2 factorial over 4 minus 2 is 2 factorial. And so that's going to give me 4 times 3 over 2, which is going to be 2 times 3 is 6. So that will be 6x squared delta x squared. And now it's going to revert back. We'll get these two terms again. So we'll have plus 4x delta x cubed plus delta x to the fourth. And then, of course, minus 4x cubed here on the end. That and this will cancel. All of this is divided by delta x, but we can just divide that out right here, taking 1 off of each, turning this into 2, and this into 3. And the limit as delta x approaches 0 on this. This goes to 0, this goes to 0, and this goes to 0. And so all I'm left with is 4x cubed. So f prime of x is equal to 4x cubed. Pretty straightforward, huh? All right, the last thing I want to consider is differentiability. That's a tough word to say. But let's consider the function f of x equals the absolute value of x minus 1. Now, what does that look like? Well, remember what the function f of the absolute value of x looks like, right? It's like a v about the origin, right? So x minus 1, that just transfers everything to the right by 1. So at x equals 1, we're going to have a v, right? It's a sharp corner right there, yes?
Yeah.
Now, what does your insight tell you about the derivative at 1? Does it exist? Is it differentiable? Well, think about it, right? What does the slope, right? We see what the tangent line is going to be on the left-hand side, right?
Yeah.
It's a constant, yes? Because this is a straight line, right?
Yeah.
So, but it's negative. It's a negative slope, isn't it?
Yeah.
And but coming from the right, approaching 1, we have a positive sloped derivative, yes?
Yeah.
And so what we end up getting here, you can see that we've got negative slope and a positive slope. It's never equal to 0, right? So we would have to guess that this derivative doesn't exist and that it's not differentiable at this point, x equals 1. But let's see if we can show that using our limit notation. This time we'll use formula number 1. So the limit as x approaches 1 of the absolute value of x minus 1 minus this evaluated at x equals 1 minus 0, so it just gives me that, divided by x minus 1. Well, what does this look like, right? So if I look at this from the left, let's say coming from the left, this is going to be x minus 1 will be a positive value always, but from the left, say if I had 0 minus 1, that's negative, right? So I get, a minus slope. If I were to do it from the right, the numerator is again still positive. The denominator is also positive this time too, though, right? Because say it was at x equals 2. 2 minus 1 is positive 1. So this is going to be a positive slope. So if I were to graph this, right, what does this look like? Here's x equals 1. I didn't notice that I could have just written in what the slope is here, right? If I choose, say, x equals 2 coming from the right, I have 2 minus 1, absolute value in the numerator, 2 minus 1 in the denominator. So this would be equal to minus 1. And here the slope would always be positive 1. So here's 1, here's minus 1. And so that's what it looks like. So we see that it is not differentiable. And an important consequence of that is the idea that if f is differentiable at a point, then it is continuous. So if it's differentiable at a point, then it's continuous at that point. If it's continuous at a particular point, that does not mean that it's differentiable at a particular point. Imagine something with a vertical tangent line, for example. Continuous there, for sure, but not differentiable. Okay? So if it's differentiable at a point, then the function will be continuous, but the converse is not true. One last thing I want to mention before we go. If I told you that f prime of x was a constant, let's say it's equal to 1, can you tell me anything about f of x? Got to So this tells me what the tangent line, what the slope of the tangent line of the function f of x is at any point, right? And it's telling me that it's constant. So what kind of curves have constant slopes? Parabolas? Do parabolas have constant slopes? No. Do lines have constant slopes? Yeah, so you can tell me this is the form of a line. Now, which line it is, you can't say. It could be, here's a line with a slope of 1. Here's another line with a slope of 1, right?
Yeah.
But you can at least tell me that it's a line with a slope of 1, if that's what the constant this happens to be equal to. That's going to prove useful insight in your homework, because there's a problem in there that's related to that. If you get stuck on it, let me know, but I think you'll be okay with it. So we've learned about tangent lines, what they are, by exploring tangent lines to a circle, and then using that to springboard to the idea of a secant line, which we can then take in the limit that the 2 points making the secant line approach the same point, we get a tangent line, right? Giving us these 2 difference quotients up here, right? And when we take the limit of these 2 difference quotients, right, we get the tangent line. And the slope of the tangent line we've stated is what we call the derivative in calculus, okay? And I think it makes sense because remember that the slope of a tangent line is this delta y over delta x, right? And so in the limit that the 2 points approach the 1 point, right, this approaches dy over dx. And that's the way that I've always thought of these derivatives, as these deltas, when they get really tiny, they become these little d's, okay? And so that's kind of the connection between the two.
Yeah.
Hopefully that makes some sense to you. And with that, I'll see you next time.